SwayamPrabha. Digital India. Educated India.
Hello, in this video we will be looking at the stress strain relations. The difference between the stress strain relations we will be discussing in this video versus what we have already discussed is, this time we will try to bring some physical intuition into this stiffness and the compliance matrix. This we will do by writing them in terms of these engineering constants which we are mostly familiar with. So, just to summarize, to recap, last class we showed these are the stress strain relations and the strain stress relation for an orthotropic material. And maybe I should repeat it again, since we see that most of the components are going to 0, this is actually for a specially orthotropic material where the coordinate system chosen is aligned along the 3 principal directions. Okay. Having said that, now in this video we are more focused on to bring some physical intuition into these stiffness components and the compliance components. The way we do it is through engineering constants. So, we are familiar with engineering constants such as elastic modulus E, shear modulus G, or the Poisson ratio nu. But we are more familiar with the isotropic materials where we just need to write E, G and mu and it should suffice. But when we are talking about orthotropic materials, we need to add some suffix. The reason is because if we are discussing about the elastic modulus E, this value of E depends on the direction. So, for example, E1 means the elastic modulus in direction 1. Similarly, I can write E2 and E3 which represents the elastic modulus in the directions 2 and 3. Similarly, we can also discuss about this shear modulus. Where again we should write it in terms of the planes such as G12, G23 or G31. And lastly, the Poisson ratio which we represent as nu ij, we are calling this as the Poisson ratio. Here we need to be clear about what is the definition of Poisson ratio. So, we say that this is negative of epsilon j by epsilon I, where assuming that the loading is in I direction. So, let us say if we are loading in this ith direction, then the ratio of the strains in the jth direction by the strain in the I direction is given by this Poisson ratio nu ij. For example, what it means is, let us say we are talking about nu 1 2, which means we are talking about a load in the one direction and the ratio is nu 2 by epsilon 2 . So, it will be epsilon 2 by epsilon 1. So, the numerator is the direction which we are interested in, the denominator is the direction where the direction of the load is applied. Okay. Here there is one more point we need to add, saying that nu 1 2 may not be same as nu 2 1, because according to our definition nu 1 2 and nu 2 1 have different directions, because for nu 1 2 we are talking about loads in direction 1, but when we say about nu 2 1, we are talking about loads in direction 2 and we are looking at strains in direction 1 and 2. So, we will come back to this in a minute, but now let us proceed by seeing how do we get these engineering constants. So, the way we will do it is we will consider few experiments. So, let us start with an experiment where let us say we are only looking at this block in the 1 2 plane. Let us say sigma 1 is the only applied load. So, for this load let us say it deforms to a new position, something like this. Since we are discussing about an orthotropic material, we see that there is no shear extension coupling. Therefore, because we are applying only a normal stress, we only get a normal strain and there is no shear strain involved. But now let us try to see what are the strains we get. So, let us start with epsilon 1. What is epsilon 1? Epsilon 1 according to this equation will be S11 times sigma 1. But now let us try to introduce the engineering constants. According to our definition, let us say E1 is the elastic modulus in direction 1, then how can we write the strain? Strain is sigma 1 by E1, right. So, where sigma 1 is the stress in direction 1 and E1 is the modulus or the elastic modulus in direction 1, fine. So, from this what we can say? We can say that S11 is simply 1 by E1, right. Now, let us move to the second strain. So, since we have seen we have applied the load in direction 1 and in the direction 2 there is a change in the shape or there is a transverse strain. How do we represent the transverse strain using this strain stress relation? We can write it as S21 times sigma 1, right. So, this is the S21 times sigma 1 is the only non-zero stress. So, the rest all are going to 0, sigma 2, sigma 3, these all are 0. So, only S21 will bring in the strain epsilon 2. But how do we write this epsilon 2? Here we can use the definition of Poisson ratio and write it as so previously we said we can use this nu 1 2 where the loading is in one direction, then we said the according to definition it is epsilon 2 by epsilon 1. Now, since we are looking at epsilon 2, we should be able to write it as minus nu 1 2 times epsilon 1. But we have just seen what is epsilon 1, let me plug in here. So, I can now write it as nu 1 2 divided by E1 times sigma 1. So, we have replaced this epsilon 1 with sigma 1 by E1. So, if we look at this, we should be able to now write what is S21. S21 is minus nu 1 2 divided by E1, fine. Similarly, though here I am only showing you in 1 2 plane, we are considering a 3 dimensional object. So, of course, there will be a third component of the strain as well, and this component of strain from the strain displacement strain stress relation we can write it as S31 times sigma 1, and from these definitions of Poisson ratio I can now bring in this Poisson ratio nu 1 3 which is minus epsilon 3 by epsilon 1. So, with that definition I should be able to write epsilon 3 as minus nu 1 3 times epsilon 1, and again I can use this definition of epsilon 1 which is given here. So, if I plug in that it should be by E1 times sigma 1, and now looking at these relations S31 times sigma 1 and this constant times sigma 1, I should be able to write S31 as minus nu 1 3 by E1. So, we notice that from this single experiment where we have only applied a uniaxial load in direction 1, we are able to get 3 components of the compliance matrix. We are able to get S11, S21 and S31. Fine. Now, let us move into a second experiment where instead of applying the normal load in direction 1, this time we will apply it in the direction 2. So, let us say this is sigma 2 and sigma 2, and we are also saying that this is the only non-zero load acting on the material. Then we expect the deformation to be something like this. Okay. But now we are interested in writing out how we can write the different strains. So, this time let us first look at epsilon 2, because since sigma 2 is the only non-zero and the rest all are 0 applied stresses. So, we can write epsilon 2 as S22 times sigma 2. But once we bring in the elastic constants, here I can bring in this elastic constant E2, where I can say it is sigma 2 by epsilon 2. From this definition I should be able to write this, replace sigma 2 as, we can now write this as sigma 2 by E2, simply because here I can replace sigma 2 by E2. Fine. From this relation now I should be able to write what is S22, which is simply 1 by E2. And now let us look at what is epsilon 1, or the strain in direction 1 because of applied load sigma 2. How do we find that? Here we write it in terms of S12 times sigma 2. And from the Poisson definition, here we will bring in this Poisson definition of nu 21, meaning the loading is in the direction 2. This should be written as minus epsilon 1 by epsilon 2. So, now epsilon 1 is simply minus nu 21 times epsilon 2, and here we will bring in this definition of epsilon 2 and now rewrite this as nu 21 by E2 times sigma 2. So, from this expression one should be able to write what is S12. S12 is simply minus nu 21 by E2. And now let us move into the third component of the normal strain, which is epsilon 3. Epsilon 3 should be able to write it as S32 times sigma 2, which again from the Poisson definitions, let us say we are now defining loading is in direction 2 and we are looking at 3. So, it is minus epsilon 3 by epsilon 2, which means I should be able to write this as minus nu 23 times epsilon 2, and this epsilon 2 I should be able to write from the second equation, which is minus 23 by E2 times sigma 2. So, from this expression again I should be able to find out what is S32, which is minus nu 23 by E2. So, now we are able to find 3 more constants, which are S22, S12 and S32. Fine. So, in the previous slide we have done an experiment where we applied a uniaxial load in direction 1 and got three of the compliance components, and in this slide we showed when the uniaxial load is in the direction 2 we got 3 more components. But there is an important observation to be made. So, here in this slide we showed what is S12 and in the previous slide we have shown you what is S21. So, let me write it down in the next slide. S21 is minus nu 12 by E1. But we know that the compliance matrix is symmetric, which means S21 equals S12. So, since we know that it is a symmetric matrix, we should be able to write this as, from here we should be able to write it as minus 21 by E2, and this is a very important observation. Let me show it in a box. So, here what we see is we have two Poisson ratios nu 12 and nu 21, and then we also have two elastic constants E1 and E2. So, what it means is, let us say if we are writing for nu 12, it can be written as nu 21 times E1 by E2. So, usually when we are talking about isotropic materials, we do not bother to write the subscript, but when we are discussing about the orthotropic materials, the subscripts are very important, especially for the Poisson ratio, because this shows that nu 12 is not equal to nu 21, especially when E1 is not equal to E2. When there is a special case, when both E1 and E2 are the same, that is the only time when we have both the Poisson ratio nu 12 will be the same as nu 21, but this is only possible when E1 equals to E2. Okay. But coming back to our discussion about engineering constants, from this experiment we are able to show you three more components of the compliance matrix. Now, let us move into a different experiment. Now, instead of applying normal stresses, let us say there is a shear stress applied. So, now again we are talking about a different experiment. Now, let us say tau 23 is the only non-zero force. So, from looking at this expression, what are the non-zero strains which are observed? We see that there is only one non-zero strain, which is gamma 23. Gamma 23 is written as S44 times tau 23, which means S44 is simply shear strain gamma 23 by the applied shear stress tau 23, which we can replace it with the shear modulus G of 23. So, here we have shown that S44 can also be written in terms of the elastic constant. In this case, it is the shear modulus G23. So, similarly, I can have another experiment with another shear stress. Let us say this is tau 1 equal to 0. This should give me S55 as 1 by G of 31. And similarly, I can also do one more experiment. Now, this time tau 12 is the only non-zero shear stress applied. Then S66 can be written as 1 by G of 12. So, let us see what are the components we are able to write here. Okay. So, what we have shown in the last two slides and in this slide is, we can think about several experiments, simple experiments where the loading is there is only one non-zero stress component, and then we are able to find at least one component of the compliance matrix in terms of the elastic constants. But since we are discussing about an elastic material, we can apply superposition. So, when we apply superposition, meaning that In the first experiment, it is only uniaxial in the direction 1. In the second experiment, it is uniaxial in direction 2. Similarly, I could have done another experiment uniaxial in direction 3, and the 3 different experiments we have done with one shear stress in each of the experiments. So, if we bring all those 6 experiments together and then we replace the compliance terms, now we get these compliance matrix, because we have said that strain is written as compliance matrix S times the stress. So, in this compliance matrix we are able to write it in terms of the elastic constants E1, E2, E3, as well as the shear modulus G23, G31, G12, and the Poisson ratios. So, here we have the Poisson ratio nu 12, nu 13 and nu 23, as well as the Poisson ratios nu 21, 31 and Poisson ratio nu 32. But here is a question to ask. So, here we have 3 each, but are these all independent to each other? So, which means here I have shown you 12 engineering constants. Are all of these independent to each other? The answer is no. The reason is because we have just shown in the previous slide saying that nu 12 can be written in terms of nu 21, it is just a ratio of the other components of elastic modulus. So, which means only these first 9 are independent and the rest are dependent. The reason why they are dependent is because I can find out what is this Poisson ratio nu 21 by knowing what is the Poisson ratio nu 12 and the elastic constants E1 and E2. Since I am able to find nu 12 using the other 9 independent constants, we call this as the dependent constant. So, ineffectively we have shown for an orthotropic material using these 9 independent constants, engineering constants, we can describe the strain stress relations. Okay. So, once we know the compliance matrix, one should be able to find the stiffness matrix as well, because previously we have shown that stiffness matrix is simply the inverse of the compliance matrix. So, since we are able to write the compliance matrix in terms of the engineering constants, we should be also be able to write the stiffness matrix in terms of the engineering constants, but of course, since we are doing an inversion, that expression will be a little more complicated. But this is an important observation to say that both the stiffness and the compliance matrix can now be written in terms of these engineering constants. So, in the previous slide we have seen for the orthotropic material how we can write in terms of the engineering constants, and which is again shown in this slide here. Let us say we are talking about the transversely isotropic material. So, if we are now talking about the transversely isotropic material, some of these constants can further be simplified. So, for example, there we can see, let us say plane 2 3 is the plane where the properties are the same in any direction. Then I can write that E2 is the same as E3 and G13 So, I can write G13 is the same as G12. Similarly, Poisson ratio nu 21, I can write it as nu 31. And in addition to this, we can also say that this G23 can be written in terms of E and Poisson ratio as E2 by 2 times 1 plus nu 32. So, if we do all of these, we see that what we are left is with 5 independent constants. And this can be written as E1, E2, G12, nu 21 and nu 23. Okay. So, these are the 5 independent constants which will be left out if we are considering the transversely isotropic material. But again we can further simplify and say that we are only looking at an isotropic material. Then we can definitely show that all the 3 shear moduluses like the G12, G23 and G31 all can be replaced with a single shear modulus G, and similarly the 3 elastic moduluses E1, E2 and E3 can be written as simply E. The same thing with the Poisson ratios nu 12, nu 23 and nu 31. So, what it means is previously we were writing in terms of a subscript, but now we do not need to show any of the subscripts. So, we can use any 2 of these engineering constants. Okay. So, in summary, what we have seen in this video is we are able to write the stiffness components and the compliance components in terms of the 9 engineering constants to start with for the orthotropic material. But later when we move to the transversely isotropic material, we said these engineering constants can be reduced to 5 engineering constants shown here, which are the E1, E2, G12 and 2 Poisson ratios, nu 12 and nu 23. And lastly, if we are considering this isotropic material, we can get rid of the subscripts because these material properties can be simply written as shear modulus G, elastic modulus E and Poisson ratios nu. But since only 2 of them are independent, we can pick any 2 of these 3 and write the stiffness matrix as well as the compliance matrix. So, to conclude, in this week we have seen what is the relation between the stress and strain in the 3-dimensional stress data. But in the next week we will go into simplifying things for a 2-dimensional picture, because we will see that lamina can be considered as a 2-dimensional material, and then we can simply work with 2-dimensional stresses and strains, and we can further simplify these stress strain relations. So, see you next week where we will discuss about the macromechanics of the lamina. Thank you.